thank you very much, Yanir, and also Scott, for this really great opportunity to come back to Maryland. It's been a great pleasure and an honor. And it was very interesting to try to think through what to talk about here. So I'm going to talk again about dynamical systems and that kind of open up into a lot of interesting pure mathematics and raise from very simple starting points some difficult, open, and possibly profound questions, in addition to surprisingly entering into some modern mathematics that doesn't seem to be connected with the subject at first sight. And so I won't read through all the names that play into the discussion I'm going to give today. Let me just start with billiards. So for me today, billiards will be the study of a billiard ball moving along inside a polygonal region in the plane. Traditional billiards taking place in a rectangle, but my billiards will take place in polygons, usually regular polygons. Usually, if you think about the regular pentagon, it's already rich enough to show almost all the interesting phenomena I want to discuss. And what I want to begin with is the theory of periodic trajectories. So if you have a regular pentagon, what slopes can you start moving the billiard ball along so that you're assured it comes back to where it started eventually? If it was a square and you went along a rational slope, you would necessarily return to when you started. But what happens in a pentagon? And so let me do some experiments. So here's a picture of a fairly long trajectory in a regular pentagon. And this one is actually periodic. And one can show that there's a dense set of slopes that are periodic. And also, once one trajectory is periodic, all the parallel trajectories are periodic. So periodicity only depends on the slopes. That's not obvious, but it's true. But the naive question is, what are the periodic slopes? And also, how do these periodic trajectories behave? And what do I mean by behavior? Well, we'll see that in a second. So let me just first show you the results of some experiments. And I really encourage you to try these experiments. It's very easy to simulate billiards on a computer, and you immediately see something quite interesting. So here I'm showing you there is, in fact, a periodic slope in the regular pentagon. If you start your trajectory parallel to one of the sides, so let's call the slope of this side S, and you start at the midpoint of one of the edges, that's a reasonably convenient or symmetric place to start, then the trajectory will be an inscribed star. So it comes back to where it started after hitting 5 sides. So I'll say the combinatorial length of that trajectory is 5. So now I might try just naively multiplying this slope by an integer and see what happens. So if I multiply it by 4, this is the new trajectory. So 2 things are interesting. One is, in fact, it's still periodic, even though I multiplied by this integer, but it's much longer. The combinatorial length went up by almost a factor of 100. So let's try something more complicated. If you multiply by 20, the combinatorial length is more than 2,000, and the picture is essentially black. And if you multiply by, this capriciously chosen number 6765, then the length of the trajectory is about 1.7 times 10 to the 25. So I won't draw the picture because it's identical to this picture. But this is what you see right away is there's very simple slopes that are in fact periodic, but where the period is extremely long compared to the slope. And what that means is that if you start investigating in the most naive way, even reasonably small slopes, you can't test for periodicity by a naive computer algorithm. You don't have 10 to the 25 steps is pretty long for checking this naively. So you might wonder, how do I even know that this is periodic, let alone know the length of the trajectory. And I want to give some hint of that. So here's a theorem. So the theorem is that we know, in fact, in a regular pentagon exactly what the periodic slopes are. They are obtained by taking that initial slope S we started with, the slope parallel to a side, and multiplying by any element of the field Q adjoin root 5. And the root 5 here is not too surprising. It has to do with the fact that this is a pentagon. But then, yes? It's not flat initially. It's initially parallel to this side. So, you know, that's a line. Its slope is not infinite. It's a little bit bigger than 1, right? It's the tangent of 2 pi over 5.
I think he meant that you could have gotten the same trajectory by starting.
That is absolutely true, and the theorem is true if you multiply 0 times q root 5, but you won't get all of them. So my definition of S was on the previous slide. It's this slope. Yeah, good point. But then here's a more accurate statement. So when you want to describe how complicated the slope is, there's a natural way that people who do arithmetic do. They talk about the height of the slope, which is roughly speaking the number of digits it takes to write the slope down as a simple expression in using integers and root 5. And it turns out that the log of the length of the slope has to do with not the height of the number you wrote down here, but with the square of the height of the number. So this is expressing the fact that a relatively simple slope can have a much longer trajectory. So the height, just to give you an idea, the height of the integer n is log n. And what this is saying is that if you had a slope that was, say, on the order of 10 to the n, the length combinatorially of the trajectory might be as big as 10 to the n squared, so enormously larger. And in fact, this is sharp. So this exponent n squared can be realized by infinitely many slopes. So this ratifies our experiments, and even better, it gives us a complete description of what the periodic slopes are. Okay, so now how is it possible that we know what the periodic slopes are in the regular pentagon? It's because of this beautiful theorem of Veitch, which relates billiards in a regular pentagon. It's something you can easily discuss at the high school level of mathematics with a certain triangle group, a subgroup of SL2R, which we think of as the Mobius transformations acting on the upper half plane. It's what's called the 2-5 infinity triangle group. So this is a specific group of matrices, and there's a certain elements on the real line, which are called the cusps of this group, and the periodic slopes correspond to the cusps. And this is true quite generally for if I replaced 5 by 7, there would be a group delta 7 for which the same statement holds. And I won't say too much about the proof of this theorem except this word renormalization. So what Veitch was able to show is that there's a way to study long slopes by applying some sort of operation which relates them to much shorter slopes, much shorter trajectories. Long trajectories can be somehow reduced to much shorter trajectories by a renormalization group, and that's essentially the role of this group delta 5. So I'm showing you here the traditional picture of the action of the group delta 5 on the upper half plane. So there's a translation here, T, that identifies this line with this line. There's a Mobius transformation that fixes this point and rotates by 180 degrees. And then especially there's a Mobius transformation here that's a rotation around this point, and that element has order 5 in the group delta 5. And this region up here forms a fundamental domain for the group action, and these points that you see down here, they're almost the cusps of this group. So more precisely, I'll show you in a second, there's a kind of a circle packing in the upper half plane this group determines, and the bases of the circle correspond to the periodic slopes. So let me first, though, reflect on what the power is of Veitch's argument. What Veitch shows is that there's actually only one type of periodic billiard in the pentagon. although we're seeing all of this radical complexity as we vary the slope, up to this renormalization operator, there's only one type. And that's related to the fact that this group I'm talking about, this cusp, which will be special points on the real line, it forms a single orbit under the action of the group. So that's how Veitch's insight allowed for a really radical and deep analysis of dynamics in the pentagon, of billiards in the pentagon, and reduced it to something related to complex analysis and hyperbolic geometry. So as I said, they correspond to the cusps. This unique type corresponds to the cusp of the quotient of the upper half plane by this group delta 5. And the quotient is, here's a nice picture of what it looks like approximately as a hyperbolic manifold. It's what's called the 2-5 infinity orbifold. It can be thought of in the following way. You take a hyperbolic triangle with one vertex at infinity, another with a 90-degree angle, that's the 2, another with an angle of 2 pi over 5, and then you double it. You glue two of those triangles together, and what you get is a non-compact hyperbolic Riemann surface, or orbifold, and this place where it goes shooting off to infinity, getting very narrow, is called the cusp. And in the universal cover, the cusp will give us circles resting on the real line. Now, I want to say a little bit about this group and the number theory behind it, because to carry out a deeper analysis of dynamics in the pentagon will just require some terminology that's elementary, but let me fix it. But also, there's something very interesting about this group delta 5. You might say, is that sort of like the group SL2Z? And the answer is yes and no, and primarily no. So to address that, let me first bring in some more players. So we saw the field Q adjoin root 5 was important. The ring of integers in that field is Z adjoin the golden mean. So gamma will denote the golden mean. And sitting inside of SL2R squared is a lattice, which is this is sort of an analog of SL2Z. It's the set of 2 by 2 matrices of a determinant 1 with entries in this ring, in the ring generated by the golden mean. So this is a lattice, not in SL2R, where it would be indiscrete, but in the product of two copies of SL2R. You use the two different Galois conjugate embeddings of K into the real numbers, using plus or minus square root of 5, to map this abstract group into the product of these two Lie groups, and there it's discrete, and in fact it has cofinite volume. However, the group we're interested in is of infinite index in this group, which is reasonably well understood. And so this is what's called a thin group, and it's called a non-arithmetic group. And it's this thinness and this failure of arithmeticity that makes the analysis of billiards, the concrete analysis of billiards in regular polygons, so interesting, so rich, and also so difficult. So let me explain that a little bit, say a word about these non-arithmetic groups. They are really mysterious. This group is generated by these two elements. Again, gamma is the golden mean. And here's just another recapitulation of how it acts on the upper half plane. Here you see the 2-5 infinity. That's almost a fundamental domain for the action of the group. And you can ask yourself, what are the matrix entries that arise in this group? I mean, every element in this group is a matrix. What numbers can appear as matrix entries? What pairs of entries, pairs of numbers can appear as columns in this group? And especially, where are the cusps of this group? That just means what's the orbit of infinity under the action of this group? And the theorem is that the cusps of this group coincide with the projective line over Q adjoint square root of 5. In other words, they're everything that they could possibly be. Everything that could be a cusp is a cusp. And moreover, this is a little icing on the cake, they satisfy some sort of height bounds, and these height bounds explain the control on the lengths of trajectories that I that I alluded to when referring to the initial experiments. Okay, so here's, at long last, is the circle packing I promised you. So there's a beautiful way to recursively construct a packing of circles in the upper half plane like this. You draw a horizontal line, and then you draw two circles here that are just far enough apart that you can fit two more underneath them, symmetrically and tangent all around. So if you think of this line as bounding a circle that goes up to infinity, what you see is a necklace of 5 circles here, sort of arrayed around this particular point. But now if you go deeper, whenever you have 2 smaller circles that are tangent, there's a way to put 3 more in between them and make another 5 cycle of circles and another 5 cycles of circles and so on. So that just using the number 5, there's a way to add more and more circles to the upper half plane, adding more circles to fill the interstices of what were left by the preceding layer. And the theorem is that eventually every point in the field Q adjoin the square root of 5 lies at the base of one of these circles. That's in fact equivalent to the statement that all the periodic slopes are the ones we think they should be. Okay, now here's a related statement having to do with continued fractions. So the ordinary continued fraction of a real number is associated to the group SL2Z. You write x as well as approximately an integer plus 1 over an integer plus 1 over an integer and so on. That's the traditional continued fraction expansion of a real number. Well, I like to compute the golden fractions of real numbers. So this is obtained in the following way. You take your number and you try to write it as an integral multiple of the golden mean. And then you take the reciprocal of what's left over and you try to write that as an integral multiple of the golden mean, and so on and so on. And in fact, the theorem I just mentioned is equivalent to the statement that if you carry out this continued fraction algorithm, starting with a number in this quadratic field, Q adjoin the golden mean, it has a finite continued fraction. This process eventually terminates. And this process is very fast on the computer. However, it's not quite as fast as you might guess. The height-bound theorem says that you can bound the number of terms in this continued fraction by the height of this number s. And you can bound the size of these integers ai that occur by the height of the number s. And that makes this whole picture very effective. So not only can this continued fraction be computed for every number in this quadratic field, but it can be rapidly computed, and we know how long that computation is going to take. Okay, now I want to make a pass at this beautiful theory of moduli spaces that, to which Scott has made so many contributions, and just give you a glimpse of the deeper mathematics behind this discussion. So it turns out that the quotient of the upper half plane by this triangle group can be thought of as an algebraic curve. In fact, it can be thought of as a family of curves parameterizing a family of Riemann surfaces of genus 2. So we say it admits a map into the moduli space of Riemann surfaces of genus 2. In this moduli space, you can record the Jacobian of each of these Riemann surfaces. That's a complex torus of dimension 2. And that complex torus turns out to have a very special property. Namely, it has extra symmetries. Technically, it has what's called real multiplication, which means that this map to the moduli space here, which is 3-dimensional, factors through a certain surface. And so the image here doesn't lie in just a general position inside of M2 or A2, but it sits on a very particular surface called a Hilbert modular surface, which is canonically associated to the ring of integers in this quadratic field K. Okay, so this is the bigger geometric picture underlying this discussion of billiards in the regular pentagon. And it's by analyzing this picture in detail that that one's able to prove the theorems I just alluded to. So rather than going deeply into the details of how that argument goes, I just want to give you a statement of a theorem about curves on this Hilbert modular surface that underlies the whole discussion. So the theorem is that if you start with a real quadratic field, you have an associated surface, and the theorem is that the cusps of every curve on this surface are as big as possible. They coincide with the projective line over the associated field, and they satisfy these quadratic height bounds, which are what are controlling the lengths of trajectories. Okay, now this is a lie, because I omitted the word geodesic. And what geodesic here means that this curve has the remarkable property that it is totally geodesic with respect to a certain metric on this surface. It's a sort of extremal curve on this surface, and to be precise for the experts, it's a geodesic curve for the Kobayashi metrics on domain and range. So the curve we're interested in turns out to miraculously be one of these special types, and this general theorem explains in some more intrinsic way where the good properties of billiards in the pentagon come from. So once you've proved this theorem, all the results on billiards and about continued fractions and so on, they all follow from this theorem. So I could give you a glimpse of the proof of this theorem, but I think I'll just let you watch it go by until I get to one of the main ideas. So one of the main ideas in the proof of this theorem is, well, number theorists have a good way of measuring the heights of algebraic numbers, and they have to do with how complicated are the integers you need to describe these numbers. But when your number somehow is associated to a cycle on your surface, an element of the cohomology of a surface or an algebraic variety, that element of cohomology also has a natural measure of its size. If there's a Kähler metric available, it's what's called its Hodge norm. And the idea of this proof is to take the arithmetic data and put it together with the product of this Hodge theory data and get a method of measuring heights that's both arithmetic and geometric. And it's by exploiting this new kind of height that one is able to demonstrate this theorem for Hilbert modular surfaces. And it only works for surfaces. And the reason, roughly speaking, is that what you're trying to do is make this height go to 0 and along some sort of path on the surface. And you're able to make the first term go to 0 very fast. But the second term might grow at an equally rapid rate. Well, it turns out the second term can be proved to grow more slowly than the first term. And so you have this little competition, and the first term wins, and the theorem is proved. If we went to three-dimensional Hilbert modular varieties, if we went to cubic fields from quadratic fields, you try to carry out a similar argument. There'd be an additional term here. This would be going to 0 like e to the minus t. This a little bit more slowly than e to the t. This a little bit more slowly than e to the t. That means the product is a little bit more slowly than e to the 2t. And you might not win. And in fact, you don't win when you go to fields that are more complicated than quadratic. So I'm trying to tell you a positive story about the pentagon, but I also want to say we're skirting the boundary of our knowledge here, because if we just go to a slightly more complicated field, then this argument fails, and in fact, what happens is very much up in the air. Okay, so that was a very quick sketch of the proof of the mathematics that underlies this theorem about the pentagon. But what I really want to draw your attention to is not what we know, but what we don't know. Okay, so what happens if we try to go beyond quadratic fields? Not only may we be flirting with things that we haven't been able to prove, we may be trying to address undecidable problems. So let me give you an example of a very simple question in the theory of billiards that may be undecidable. Undecidable means there's no algorithm to settle this problem. So I learned from computer scientists that when you have a problem that an algorithm is supposed to solve, you describe it in capital letters, like clique or sort or whatever, Hamiltonian cycle. So I'm going to call this problem cusp, and it depends on an integer n. And the problem is, you're given, you have this group that's attached to the regular n-gon, like what we had for the pentagon, and we're given an element in the corresponding field concretely. And the problem is to decide if this number is a cusp of this group. Now, it turns out that this is equivalent to saying, if you take this number and you try to mimic our continued fraction algorithm, does that process eventually terminate? And so the open problem is not how to do this, but to the contrary, is it possible that for n equals 7, 9, or 11, this particular algorithmic question, cusp of n, is literally undecidable? That is, there's no algorithm to decide it, which would mean there's no computable bound on how long you have to wait to see if the continued fraction terminates, or even more simply, how long do you have to wait for the trajectory to prove itself to be periodic? So we saw you had to wait an enormous but predictable time for the pentagon. It's conceivable that for the heptagon, there's no computable bound on how long you have to wait for a trajectory to reveal its periodicity. So it's open already for n equals 7. In this case, k is a cubic field. And I've just drawn you a couple of trajectories here again. So here's the sort of analog of the star for the heptagon. I've changed my notion of slope. So this corresponds to a slope of 1 with a different basis for the real numbers. And you modify this slope very slightly, and its length becomes 10 to the 40. And you modify it a little bit more, and you don't know whether or not it's ever periodic, even using this renormalization theory. There is no known way to test for periodicity of billiards in a heptagon. So I hope this gives you some appreciation for the miracles that are happening for the pentagon, and the fact that we're skirting this complicated and possibly undecidable territory. It's very hard to prove that problems are undecidable, by the way. You know, the halting problem for algorithms is undecidable, but it would be almost unimaginable that you could reduce the halting problem to a problem about periodicity of billiards in the heptagon. And so I'm doubtful one would ever be able to prove that this is undecidable, but it may very well be the case. Okay. So let's go on to another problem. This, again, I just want to give you a glimpse of an interesting question about billiards and some of the mathematics behind its answer. So here again is a very long trajectory in the pentagon. And one thing you'll notice, besides the fact that it's pretty long, is it's quite evenly distributed inside of the pentagon. It seems to be going everywhere. It's almost uniform with respect to area measure on the pentagon. So you might ask, if you have very long trajectories, are they uniformly distributed? Now, Veach showed that if the trajectory is not periodic, if it's infinite, then it is uniformly distributed. So you might say, if an infinite trajectory is uniformly distributed, then a very long periodic one should be almost uniformly distributed. So do, in fact, the long periodic trajectories equidistribute? And the answer is no, not always. And this was first pointed out by Davis and Liliev. And they gave a really beautiful example in the pentagon. And they asked if, see, when it's not uniformly distributed, there's some sort of new limiting measure. So here's their example. Notice that the trajectory is completely missing an area in the middle of the table. You safely put your collectible Ming vase there, and you let the billiard ball go as long as it wants, and it never hits it. And moreover, you can make the period of this trajectory longer and longer and longer. So it's definitely not uniformly distributed because it always omits this particular part of the billiard table. And what they asked was, well, what can we say about the set of measures that arise that describe the limiting behavior of long periodic trajectories? Is it, for example, a Cantor set? And they thought it might be a Cantor set because they had a sort of tree-like description of the periodic trajectories. But in fact, it's a little bit different. The limit measures form a countable set. They're not a Cantor set. And it's, for the experts, countable compact sets are homeomorphic to ordinals. This is homeomorphic to a fairly simple ordinal. It's omega to the omega plus 1. And there's a set of limit measures for each possible periodic slope. Here I'm drawing things that approximate the slope of 0. And what these measures are doing is they're describing a phenomena that physicists call scarring, which is expected to hold in other kinds of billiard tables that do not have straight lines, where you see that the billiard likes to spend more time in certain areas of the table than others. But the existence of this scarring was unexpected and quite interesting to see in the case of these polygonal tables. By the way, I'm not going to go in this direction, but the physicists will also tell you that if you make your billiards quantum, then the scarring will go away. And this is called quantum unique ergodicity, and it's another really interesting open problem that arises already when we're looking at these simple billiards and pentagons. So this theorem allows one to also describe the closure of the ergodic measures for billiards in a pentagon. And just to show you how constructive this theory is, one can actually compute what this set of limit measures looks like. And I'm showing you a picture of it here, and this will help me explain what this countable set's structure is if you don't know what omega to the omega plus 1 looks like. So here in the middle, each vertical line here, each dot here actually corresponds to a possible limit measure, a description of scarring. Here's the uniform measure, which is where there's no scarring at all. And what you can see is here's something that's way off from uniform measure, but it's a limit of other measures that get closer and closer to it. There's actually a lot of dots on these lines which appear to be continuous. You can see on the bottom. So this is actually a limit point of measures. And then here we see a limit of limit points where these vertical lines accumulate here. And then we see limits of limit points, and so on and so on and so on. But at the end of the day, if you take limits of limits of limits of limits of limits, you ultimately converge to uniform measure. That's what this structure omega to the omega plus 1 says. Okay, so there's a really rather interesting and rich structure to the failure of uniform distribution for billiards in polygons. And something that's quite miraculous is, in fact, there's a way to take 2 of these limit measures and multiply them and get a new limit measure. And this was quite surprising. And again, I'll just give you a glimpse of some of the hidden structures behind it. Again, this structure is found by considering this quotient Riemann surface, the quotient of the upper half plane, by the group associated to a regular n-gon. And in this quotient Riemann surface, there are geodesics that begin and end in the cusp of the surface. You can put those together into a category, which can be thought of as the category of non-abelian modular symbols. And it turns out that that category has a topology, and the morphisms in the category are homeomorphic to omega to the omega. And that's the ultimate source of this countable but rich structure to the limit measures for billiards in a pentagon and more generally in a regular n-gon. Okay, third question. Combinatorics, congruence, and chaos. So there's another property of periodic trajectories that's also already interesting to investigate in the case of a pentagon. And remarkably, although people have looked at billiards in the pentagon for decades, I don't think this property was observed for a long time. So let me let me show you what happens. Somebody suggested we do slope 0. So let's consider all of the trajectories that start out with slope 0 in the regular pentagon. And I'm going to start at the midpoint of an edge. Now there's 5 edge midpoints. So actually, once you tell me the slope, I have 5 trajectories to look at, not just one. So if I start here and I move horizontally, the billiard trajectory gives me an upside down pentagon. If I start here and move horizontally, I see a star. If I start at the bottom edge and I move horizontally, I run into one of the vertices of the pentagon. So I don't know what to do when you hit the vertex. So I'm going to just stop. I call that a vertex trajectory. And then, interestingly, when I move to the next edge midpoint, I see a star again. And the next one, I see the upside down pentagon again. Well, it turns out that this pattern holds for any periodic slope. There's a special edge midpoint. It's on what I call edge 1 in this picture. Here, the trajectory bounces off this edge and then hits this vertex. Or if you like, if you try to go in backwards time, you also run into that vertex. And the other 4 edge midpoints give periodic trajectories. And in fact, the 2 adjacent ones look the same up to rotation, and these 2 look the same up to rotation. And here's just another more complicated example. Here you see a vertex connection again, and then here you see actual periodic trajectories. So what we see is that if you give me a slope, a periodic slope, there's a special edge midpoint. And if you're a combinatorist or a number theorist, you can say, well, given the slope, how do I determine which edge midpoint is special? As a sort of a combinatorial question about these periodic trajectories. So which edge midpoint gives a vertex connection? And the answer is given very nicely in terms of a little number theory. The edge midpoint gives a vertex connection at a given slope if, when you take that slope and you reduce mod 2, then you get the same as the 5th root of unity raised to the kth power. So k is the index of the midpoint, and k is the power of this 5th root of unity. Both of them reduced mod 2. So to do this, you have to think a little bit about why these slopes can be reduced mod 2, why they're actually points on the projective line over this finite quotient of the ring of integers. But once that's set up, I think this is a fairly plausible, although previously unknown, way of solving this simple combinatorial problem. And it's one of the first indications that there's a deeper structure to the arithmetic of billiards in regular polygons than has been previously uncovered, because this involves reduction of the picture modulo a prime 2. And somehow there's enough information left at the prime 2 to answer this question. Okay, and that works very well for the slope for the regular pentagon. And when you can figure out the answer to this question by reduction modulo a prime or some other integer, we say that the location of the vertex connection is a congruence invariant, because it only depends on the reduction of the slope to some element of this finite projective line. This is finite because the ring, OK, mod 2 is a finite ring. So I was studying this combinatorial problem experimentally as usual, and it worked very well for the pentagon and for the 7-gon. It's a little tricky for the 9-gon. It also worked. Then I discovered it worked very well for all even numbers. So then I decided to daringly try the octagon, and everything went well. And then I tried the dodecagon, I guess this is called, the case of n equals 12. And what I discovered was I could not predict where this special vertex connection would be. And in fact, this vertex connection tends to looks as if it behaves randomly or even chaotically. So somehow hidden in the combinatorics of billiards for certain values of n, there's some form of what might be called arithmetic chaos. And to indicate how chaotic it is, let me remark this integer k that labels the special vertex connection, it can be either even or odd. So if I take -1 to that k, that's a number that's either plus or -1. Now, suppose I generate a walk on the real line by just going positively when that number's odd and negatively when the number's even, or vice versa. Then it looks like this. It looks exactly like a typical random walk. And if this had been a congruence invariant, this walk would have been periodic. So not only is it not periodic, but it's exceedingly chaotic. And as in the case of the previous talk where we were discussing area preserving maps on surfaces, there are 10 conjectures you can write down about this arithmetically generated random walk, and we don't know how to prove any of them. So for example, the simplest thing would be to prove that the ratio of W of t to t tends to 0. In other words, if there's random walk has no drift, it asymptotically has mean 0. And even that kind of thing is open. Let me just say a bit again about the more mainstream mathematics that this connects to. So first, this theory of these vertex connections has something to do with the monodromy action on the Weierstrass points of a family of curves of genus 2. And it's an instance of the idea of taking, when you have a family of curves, of taking a representation from the fundamental group at the base of the family into, well, in this case, it's SL2 of A OK mod Li. This can be thought of as the action of monodromy on the cohomology of the fibers over a finite field, or an extension of a finite field, or over a finite ring. And it can be compared to what people study in the theory of elliptic curves. There, the fundamental group is replaced by the Galois group of Q bar over Q, and you have an action of the Galois group on the torsion points of the elliptic curve. That gives you a so-called Galois representation into GL2 of Z mod Li. So notice how similar these two things look. And indeed, to analyze this arithmetic chaos more completely, one can import into the theory many of the techniques that were developed by Serre, Ribbit, and others who work on the theory of Galois representations attached to elliptic curves over Q. This is what I call the adelic perspective. So you'll remember that this thin group has infinite index in this arithmetic group. So this is hard to understand. This is much better understood, but the index is infinite. So there's a big gap in our understanding. But it turns out that if you form the profinite completion of OK, so then this becomes a locally compact group, and then you take the closure of this infinite index subgroup inside of there, it's a finite index. And so from a more arithmetic perspective, this gap moves from being infinite to being finite, and a very natural question arises, which is, what is this closure? And this question appears to be very difficult, except for Frank Caligari, who stumbled on my paper about this and within 6 months had computed exactly what this closure is. So there's one of the nice things about this discussion that emerges from billiards is it suggests interesting questions in number theory that are accessible to experts in theory of Galois representations and these kind of adelic questions. So we now know the answer to this question, and we know we can prove that, in fact, the vertex invariant for the dodecagon is not a congruence invariant, but we can't yet prove any of the apparently chaotic behavior that occurs there. And in fact, we have an exact classification of when that strange behavior arises. The next case would be, let's see, you have to be 0 mod 4 and not a power of 2. So that's 20. So the 20gon also exhibits this behavior. OK. So far in this talk, I started with 3 elementary problems in billiards, and then in each one, I started digging into the mathematics, and it got fairly deep. I now want to discuss something that seems, at least initially, unrelated to everything I've talked about already. And that means if you haven't really been listening, you can start again now, just sort of refresh. So this is a almost completely independent discussion. It's not about the regular 12-gon, it's just about triangles. And at the end, I'll try to explain why this independent sounding discussion, why this complement is actually motivated by the discussion we've had so far. Okay, so here's the interesting thing about triangles for me. So a triangle is determined by giving 3 angles. But I'm not going to require that the sum of the 3 angles is 180 degrees. When it's less than 180 degrees, the triangle wants to be hyperbolic. It wants to be a negatively curved triangle. When it's more than 180 degrees, it wants to be a spherical triangle. When it's exactly 180 degrees, it's content to be a Euclidean triangle. So the triangle's angles know what kind of geometry the triangle wants to live in. So here's a famous example, the 2, 3, 7 triangle. So this means the angles are pi over 2, or 90 degrees, pi over 3, and then pi over 7. If this was pi over 6, this would be a 30, 60, 90 triangle. But since it's pi over 7, the angles add up to slightly less than 180 degrees. And this triangle can be used to tile the hyperbolic plane. So this is the famous tiling associated to the 2, 3, 7 triangle. There's an associated reflection group and its index 2 orientation preserving subgroup that have certain extremal properties that I won't go into. That there's these beautiful Escher-like pictures associated to the triangles when they happen to be hyperbolic. Okay, so angles determine triangles, and triangles can be hyperbolic, Euclidean, or spherical. So what is the moduli space of all triangles? How can we put all triangles together into one collection? It's very simple. A triangle is a triple of angles. So we give a triple of angles, which is an element of a 3-dimensional torus. And I like to choose my numbers here to be rational in the case of roots of unity. So I'll use AI to denote the angle, but it really means the angle pi times AI. As in the previous 2, 3, 7 business, I'm kind of suppressing the pi's throughout. So this triangle can be spherical, Euclidean, or hyperbolic. Now, Galois theory comes back into this picture. If the angles correspond to roots of unity, then you can act on them by the Galois group of q bar over q. So every triangle has many Galois conjugate triangles. Now, if you don't like Galois theory, you don't have to say it that way at all. This torus is a group. And the interesting cases, the root of unity cases, just mean that these 3 numbers they're each torsion elements of S on S1. They're finite. They have finite order on the circle. And if all 3 of them have finite order, then that's a torsion point on this 3-dimensional torus. And once you have a torsion point of order n, you can raise it to a power k, and it'll still be torsion of order n, provided k is relatively prime to n. Okay, so once you have the cyclic subgroup generated by A, you can take any other generator of that subgroup and consider that to be a cousin of A. They sort of live on equal footing. So that's what we call the Galois orbit of a triangle. So this is already kind of interesting. We started with geometry, and now triangles have arithmetic cousins. And you can ask your cousins about their political persuasions. And so what I like to do is say, once I'm given one of these angles, I look within the Galois orbit and I ask how often the cousins are spherical. And we compare that to the total number of cousins. So the total number of elements in the Galois orbit. And I call this the ramification density. It's a number between 0 and 1. 1 would mean this triangle is spherical and all its Galois conjugates are spherical. There's a reason this is called ramification, which is that spherical triangles correspond to ramification in quaternion algebras. I'll just leave it at that. The terminology is justified in some way, but these are numbers between 0 and 1. And so we can ask ourselves what numbers arise as these ramification densities. And here's the interesting fact. There are constants, one greater than 0 and one less than s, such that either this density is 0 it's less than 1, or it's bounded away from 0 by rho h, and it's bounded away from 1 by rho s. So this number can't be arbitrarily close to 0, and it can't be arbitrarily close to 1. I hope you find there's some resonance of this phenomena with this question about Lamer's number. Lamer's number was about a small Salem number. We couldn't find a way to get this Salem number arbitrarily close to 1. Here, there's no way to get this ramification density arbitrarily close to 0 or arbitrarily close to 1. So I call these spectral gaps, and I know experimentally what their exact values are, and I'm very far from having a proof of that. So the proof that these constants exist is very soft. It's an equidistribution argument. Probably the interval is 1/12 to 4/5. Okay, so, and by the way, there is a good argument that for typical values, the density should be about 1/3. You have this sort of a 1 chance in 3 of being a spherical triangle. Again, I'll just wanted to allude to the fact that there's some sort of equidistribution argument that is hidden in the proof. And rather than show you those details, I want to show you a game I had to learn how to, I had to solve for, to complete this proof. So there's some sort of set of exceptional triangles you need to locate to complete the proof of this theorem. And I finally found a way of saying what the problem is one has to solve in a way that's easy to communicate, not on paper, but in a room with a movie. So this game is what I call the moving tablecloth game. So here's the tablecloth. It has this kind of plaid pattern. And what we like are these green and blue regions. And what we don't like are these yellow regions. Okay, now here's how you win the game. You have to take a ball and put it on this table and roll it so it moves at uniform speed along a straight line and never goes into the yellow. Now it's allowed to hit the edge of the yellow. I don't mind that, but I don't want it to ever go into the interior of the yellow. I want it to be exclusively in the green and the blue. So can anyone suggest a strategy for rolling a ball across this table so you never hit yellow? Oh, excellent. Okay, so that's right. So if we go along the diagonal, I think this is kind of magic that I already have the answer programmed. So if we go along the diagonal, then indeed, we always avoid the yellow. And that's one of the exceptional cases one needs to study in proving this theorem about triangles. Is there another solution to the problem? Another way to win the game? Yeah. Okay, so look at how slow this is going. It's really, I'm looking for solutions like that. Yeah? Well, this is not a straight line. Anyone else? So remember, you're allowed to be on the edge as long as you don't go into the interior. That's a hint. Yes? No, you're not allowed to bounce. This is no longer billiards. So going vertically doesn't quite work, right? So if I try to go vertically here, I'm in the yellow. And if I go vertically here, I'm eventually in the yellow. But something almost like that works. Is anyone? Where is the safety region here? The safety region is, of course, when you're deep in the green, but also when you're on this interface when you're on this line here, this moving line between that's the boundary of the blue and the green and the yellow. As long as you're on that line, you're not in the interior of the yellow. So can you find a way to stay on that line? Well, yes, of course. So what you can do is you can just move vertically at the same rate as that line is moving vertically. So whoop, see, I carefully avoided those moments when I might have gone into the yellow, bloop, and then I just make it across to the next to the next blue. So I never went into the interior of the yellow. Okay, and then the one thing that's hard to explain in a paper, but which is easy to persuasively convey here, is that there's one more solution, which is slightly more unexpected, which goes like this. So here I'm going through the midpoint, just when the blues touch. So you see, I go through a corner and then through the midpoint and then keep going. Okay, and then one has to prove that these are in fact the only ways to win the game. And that's what's needed to complete the analysis of this, the proof of this spectral gap. Okay, so now let me just say a reason this spectral gap is interesting. So it implies that for all but finitely many triangle groups, the number of spherical and hyperbolic cousins, the number of spherical and hyperbolic places of those groups are about the same. And this has a corollary, has two corollaries, one of which is very famous. So the first corollary is that there's only finitely many arithmetic triangle groups, at least co-compact arithmetic triangle groups. This was proved by Takeuchi in the 1970s. And there's a much less well-known corollary that there's only finitely many totally hyperbolic triangle groups. What this means is you have a triangle group that's hyperbolic, the sum of the angles is less than 180 degrees, and all of its cousins have the same property. And there's let me skip the examples and just show you the lists. So here's a list of Takeuchi's groups. There's 76 co-compact arithmetic triangle groups. This is taken from an appendix to the book of McLaughlin and Reed on arithmetic hyperbolic geometry. The other guys are not as well known. There's 11 known totally hyperbolic triangle groups. And I've shown them all here. The most interesting is this very last one. The numbers are worth remembering in case you run across them again. They're 14, 21, and 42. Unfortunately, as I mentioned, the proof of the preceding theorem is ineffective. So I don't know what the spectral gap actually is, and I don't know whether or not this list is complete. But I discovered something very interesting once I started wondering if this list is complete, which is that, so I wanted to answer this question, am I missing any examples in my list? And what I discovered is that while mathematicians have been running Magma and Mathematica on their desktops, the biologists have been constructing enormous computing centers. Harvard's is in a town called Holyoke in Massachusetts, which is on the Holyoke River. It's an acre-sized building filled with computer service. It uses the hydroelectric power from the river to power the servers. It uses the water in the river to cool this enormous number of hot CPUs. And you can log on to it if you probe a little bit and send the email to the right place. And this computing facility is used to solve problems like protein folding and so on that are enormously difficult compared to the problems we solve in mathematics. So to investigate this problem, I found out how to log onto this server, and I did a computation. and I proved that there are no other purely hyperbolic triangle groups, at least with P, Q, and R, less than 5,000. And if you think about it, 5,000 times 5,000 times 5,000 is about 125 billion. For each one of those, you have to test these numbers that are relatively prime to the least common multiple of those three numbers. That multiplies it by an additional factor of perhaps 1 billion. So there's maybe 1 billion squared computations to be performed if you do it naively. It turns out there's a way to randomize the algorithm and do it a little bit faster. But with access to this facility, I verified this in 30 minutes using 5,000 CPUs running simultaneously in parallel. So I think there's an enormous amount of computational experiments that can now be performed by mathematicians using these facilities that were constructed by scientists to do brute force solutions of much more complicated problems. And I was kind of proud of doing this computation until last week when Frank Gallegari also sent me a proof that in fact there are no other examples besides the ones that I've already found. Okay, so let me finish by just saying that the reason I was interested in finding these things is that I had some theorem about curves on Hilbert modular surfaces, and one could ask if that theorem generalizes to higher dimensional varieties. And using that very special example of 142142, I was able to give a counterexample to that theorem using it's defined over a field of degree 6 over the rational numbers. So I hope here's the final. I wanted to do this very concretely, so I actually have a picture of this embedding of this particular triangle group into this product of 6 copies of the unit disk, which is the universal cover of this Hilbert modular 6-fold. In any case, there's a conjecture that this is the only way to make such constructions, and what it means is that in some sense, once you're beyond quadratic fields, the Jacobian of curves is not rich enough to solve the kind of problems concerning cuffs that we're interested in. So I'd like to end by just saying I hope I've convinced you that the theory of billiards in the pentagon itself is very rich and worth studying. Okay, stop there. Yeah.
If you take instead of a regular pentagon a generic pentagon, is there much known? Like, I guess in particular, I was thinking about your question too about equidistribution of the long orbits.
Yes.
Is it possible that for a generic pentagon, is it known if the orbits actually do equidistribute?
Right. So the question was, what happens with more typical polygons, say a more typical pentagon? So there's 2 types of more typical pentagons. So one is a pentagon that let's see if I can draw this correctly. Okay, so it's not regular, but these angles are all 2 pi over 5. There's a pretty good theory for pentagons of this type, and more generally for polygons where the angles are rational multiples of 2 pi. And the reason is that when you unfold these, they give rise to compact Riemann surfaces. And then this whole theory of moduli spaces and tectonic theory kicks in. However, what if by a regular pentagon you meant just a 5-sided figure with random angles? So there's another embarrassing open problem, which is if you take a triangle, does it have even one periodic billiard trajectory? So this can be proved when the triangle is acute. It's the so-called pedal triangle, which is the path that goes between, touches all 3 sides and otherwise has minimal length. That's a billiard path if the triangle is acute. But for obtuse triangles, even the existence of one periodic trajectory is unknown. So we're really capitalizing on the fact that we're mathematicians, i.e. roots of unity are amenable to study in cyclotonic fields and Riemann surfaces. Generic polygons are very mysterious, even in the case of triangles. So I'll just say, some of you may know that this angle here, if this angle is less than or equal to 110 degrees, then Rich Schwartz, also using massive computer effort, proved that there's always a periodic trajectory. Questions, anybody? Well, let's thank us. Okay.